recap of chapter 4, but I will say it's going to be a bit of a long one, so just hang in there with me. I'll try to keep it as short and sweet as possible. So we are talking about 6 different simple machines that we have, and we'll also briefly talk compound machines. But we're going to talk about each of those types. Some of them have a little more detail than others, but we will get into those and make sure we understand them. So, first one we have is levers. A lever is a simple machine that consists of a bar that pivots at a fixed point called a fulcrum. So, levers are typically used to apply a force to a load, and there are 3 different classes based on the location of the fulcrum, the load, and the input force. So we're going to go through the next 3 slides to help you understand what that means. On me, so I'll draw a little bit better in class to show you examples of these, but I'll try to explain as best as I can here. A first class lever has the fulcrum in between the input force and the load. So what I want you to think about is a seesaw. This is one that's really easy to picture. So if you think about a seesaw, you have a board and then there's some kind of triangle wedge in the middle. That triangle is the fulcrum. That's the point where the bar is attached. The input force would be somebody pushing down, like if they're putting their weight on it, and the output force would be the other side going up. So the forces are on the opposite sides of the fulcrum. The fulcrum's right in the middle. It's the same as when someone paddles for a kayak. You have 2 paddles on each side of that oar, and as you move, your hands are the fulcrum that are in the middle, and the oars on each side as they move is putting the force on there. So keep that in mind. That's a first class lever when the fulcrum's in the middle. So an example of this would be a bottle opener. Or a wheelbarrow. I think a wheelbarrow is a little easier to picture. So a wheelbarrow, you have the load that's inside the wheelbarrow itself. That is what you were trying to do work on. The fulcrum, in this case, would be the wheel, where the wheel is attached to the wheelbarrow. So that's the point where the wheelbarrow itself is the lever. The part where the wheelbarrow is attached, or the wheel's attached, that's the fulcrum. So you have fulcrum at the wheel, the load is in the middle, and the input force is being put in where you lift it up with your hands. So in this time, the load is in the middle of the lever. So that's the second class lever. Itself, it's the weight that you are lifting. The input force is the lifting of your forearm that's in the middle there. So the difference between our 3 classes of levers is what's in the middle. First class lever, it's the fulcrum like a seesaw. The second class lever, it is the load like a wheelbarrow. And the third class lever, it is the input force like bicep curls. That has a straight slanted surface. It makes our work easier by increasing the distance that we have to go, but it decreases the force. So if you think about pushing something up a ramp, that's definitely the best example we have of an inclined plane. You have to push it farther, but you have to put in less work to push it up. So the longer the inclined plane is compared to the height, so the more shallow it is, the greater its mechanical advantage because you have to put in less input force. So to find the mechanical advantage of an inclined plane, we just have to take the length of the ramp divided by the height of the ramp. So the longer it is and in length, the shorter it is in height, the more you're going to get out of that inclined plane, the more advantage you have. Isn't confused, but basically with an inclined plane, but basically what a wedge is it's a double inclined plane that moves. So it's like having two inclined planes back to back to create a point. So a good example of this is any kind of blade, a knife, a sword, even zippers. If you look, there's they form a little bit of a wedge. The teeth of a zipper, those are all considered wedges. The longer and the thinner the wedges, the greater the mechanical advantage. If you have ever seen knives with cooking and stuff, the longer and thinner the knife is, the easier it is to cut. It definitely gives it a more of an advantage. So if we have more length and it's thin, it's going to slice more easily, which means that machine has more of an advantage. We have to put in less force in order to get that machine to work. I've played this wrapped in a spiral. The best example of this would be a screw itself. And then also things like jar lids. So anything that has those threads where you screw it on, that's a screw. The longer that the spiral is and the closer together the threads, the greater that mechanical advantage is going to be. So if you've ever done any building and you were to look at the threads of a screw, if you had ones that only had where the threads wrapped around a couple times, that screw's not going to hold very well. It would take more effort to screw in and it wouldn't hold as well. If you have a screw that has lots of threads and it's wrapped really tightly, it takes less effort for you to push it, for you to screw it in to begin with, and it also is going to hold better because it has a higher mechanical advantage. Sometimes the wheel can be a crank, like a fishing rod. So if you've ever been fishing and you've got the rod, the reel on the rod, as you turn it, you are cranking a wheel and axle. Sometimes the wheel and axle is like a knob, like a volume control. When you turn that, when you turn a volume control on your radio in a car, that's considered to be wheel and axle. Obviously, things with wheels like cars and bikes, those are all considered wheel and axles also. I just had a couple of examples that were ones that aren't as easy to think about. So things like doorknobs, those are wheel and axles. Ferris wheels are wheel and axles. Steering wheels are wheels and axles. So they're all considered wheel and axle. With wheels and axles, the larger the wheel compared to the axle is going to give us a greater mechanical advantage. So we take the radius of the wheel divided by the radius of the axle to find out its advantage. So the bigger that the wheel is compared to its axle, the less work you have to do. And our last type of simple machine is called a pulley. So a pulley is a simple machine consisting of a grooved wheel that holds a rope or a cable. The load is going to be attached to one end of the rope. The rope is slung over that pulley, those wheels, and then the input force is applied to the other end. So think about a well. If you have a bucket on a pulley, you pull the rope down, and it's going to make the bucket go up. So you apply an opposite force. An elevator is the same concept. It is a pulley. The strings on your curtains or on your blinds on your window. As you pull those strings down, a pulley causes the curtains to go up. Those are all pulley systems. We have two different kinds of pulleys. One is called fixed and one is called movable. It does not move. It's in a fixed place. Example of this would be an elevator. So as the weight moves one way, that's going to pull the elevator the opposite way, and it's attached to a specific spot. I don't have an exact example of this, but it's attached to an object that is being moved. So it does not change the object's force or the object's direction, but it is going to change the increase of the force that is on the object. Block and tackle. And essentially this is when we have two different types of pulleys together. So we have a fixed and a movable pulley that are used together. The more pulleys you have together, the more mechanical advantage that you have, because you have more machines that are able to work together, which means there's less input that you have to put in compared to output. Compound machines. So everything we just talked about are simple machines. A compound machine is when you have a machine that's made up of two or more simple machines, which is a large majority of the machines that we have out there. So I have a couple here just as examples, and then we will be looking at with a worksheet trying to identify simple machines that are in the classroom within our compound machines. But some examples I have are can opener and scissors. So can opener has three different simple machines in it. If you're looking at a handheld one, a wedge because of the blade, that blade on it that opened the can as a wedge. A lever because of the handles. When you open those handles, they're acting as a lever. And then the wheel and axle is this part that you have to spin. Scissors have two different simple machines. They have a wedge for the blade and a lever. As you move those back and forth, it acts as a first class lever. The fulcrum's in the middle that attaches the two parts of the scissors, and then you're moving those up and down. So the more moving parts a machine has, the lower its mechanical efficiency because of friction. The answer to almost anything. If you don't know the answer to something, guess friction. That's probably it. We have friction, so the more parts you have, the more parts that you have touching, which means there's more friction, which means more the energy is going towards that rather than the work that's being created. So for compound machines, the efficiency is definitely lower than what it is for simple machines. But we're going to take a look at these actually in class coming up here.